Hello, good morning again. Thank you for attending our webinar today. My name is Dharmesh Patel and I'll be giving you an overview on stack optimization program of a typical sulfur recovery unit. At a glance, we'll cover following 5 topics today. First is an introduction about SRE and basic function of incinerator, why optimize the incinerator, steps required in doing the optimization, and case study. After that, we'll follow up, wrap up, and question and answers. So, introduction. Let's talk a bit about SRE. Since 1998, Sulfur Recovery Engineering has helped refineries, gas plant, and engineering companies worldwide to achieve the optimum performance of the sulfur recovery unit. We are a specialty service firm, at first centered around the sulfur recovery unit, and now we are also providing services in amine unit and other environmental requirements and tail gas treatment units. We provide consulting services to various EPCM design firms for SRU design, engineering, and commissioning. Further, we also provide lifelong SRU servicing, which includes SRU performance evaluation, troubleshooting, shutdown, startup assistance, and debottlenecking. Our services at SRE focus on 3 main areas: testing, simulating, and learning. Here we have a brief description of our service offering. On site, we collect and analyze process stream samples, and we also assist in startup, shutdown, and commissioning. In the field of simulation, SRE tie up with VMG, which is one of the best simulation package available in oil and gas industry at present. VMG uses SRE's last 15 years of on-site testing data for different kind of sulfur recovery unit and different configuration, and VMG incorporated those data to create SRE VMG correlations. So by using VMG SRE model, we can create a model which predicts more accurate results which matches the practical performance of the unit instead of just theoretical based model. And there is one more very interesting thing over here is tune dynamic model or tune modeling. A tuning model is a steady state at the beginning. However, it matches performance of your unit on its stage of converters, reheaters, and reaction furnace. And by using that model, you can do offline study regarding troubleshooting or any cause effect analysis. Other service we provide is learning or training. SRE customize the training according to client's need. For example, if you want to customize the training for operators, engineers, designers, SRE can do that to meet your need. About me, I'm Dharmesh Patel. I'm PhD with APEGA. I'm a lead process engineer with SRE and I finished my Bachelor of Engineering in India. I have 10 plus years of process engineering experience in oil and gas industry and in various chemical manufacturing processes. I completed work at about 25 plus different sulfur plants worldwide, and I also completed 35 different projects, including troubleshooting, performance evaluation, optimization, startup shutdown, reservoir analysis, dynamic modeling of the sulfur unit, and high pressure gas analysis like LNG. Let's talk about incinerator and stack. Incinerator and stack performs in a combination at most of the SRUs. The main function of incinerator is to convert all sulfur-bearing compounds to sulfur dioxide. The feed to incinerator are tail gas stream from SRU. sulfur pit vent, and others. Other means if you have a refinery instead of gas plant, you might have some other stream coming there to the incinerator. In general, the sulfur-bearing compounds auto-ignites at 350 to 380 degrees centigrade. However, to achieve so, a higher temperature in combustion zone is needed. Typically, we achieve this thing by using fuel gas firing, and the temperature required to do so is 600 to 900 degrees centigrade. And this depends also on the capacity and the size of the plant. There were a preliminary and secondary air supply provided to incinerator. And to get the optimum value of the incinerator, we are targeting excess air at 2 to 4% at the stack outlet. However, most of the time we noticed there were poor control on this front. Air supplied to incinerator and stack by two different means. Either it's a forced draft or natural draft, and in several cases it would be combination of both. Forced draft air supply provides more precise control for the burn ratio and excess air control. Other key component at the stack is CSEM, stands for Continuous Stack Emission Monitor. Depending on location of your plant and environmental body, several locations, this instrument measures SO2 concentration in the stack as exit gas, and it reports straight or directly to the environmental body. And some stacks also have oxygen analyzer there as well. However, these oxygen analyzers so many times do not perform well because of the nature of the acidic gas, and it creates sulfuric acid formation there. So the key question is why to optimize the incinerator. There are four key parameters which drives to make us this decision. It could be one of it or it could be combination of it. The first one is to meet environmental constraint. The second to adjust change operating conditions. Third to reduce carbon footprint. And fourth to save money. So let's go and discuss a little bit more about each parameter. Environmental constraints. The environmental constraints are getting more stricter as year passes for both national and international clients. Further, not meeting those standards could lead to heavy penalty or it could warrant review on your license. The residual sulfur TRS our stack exit should be lower than 300 ppm. In other terms, like this compound consists H2S, COS, CS2. So the aggregate amount of all these components should not be above 300 ppm. And if the facility is operating less than 200 ppm, I would call it a bit conservative operation. One should strive to operate between 200 and 300 ppm. The second government constraint is ground level SO2 concentration. At specific location, we should be less than 0.02 ppm. In Alberta, many gas processing facilities are facing this problem, which is turn down, which with the reduction in the quality of acid gas, not only affects the overall recovery efficiency of the SRU, but also warrants incinerator and stack performance evaluation. To meet the environmental constraint with the turn down condition, the facility may need to revisit the old set points such as stack top temperature. Significant change in operating condition such as addition of any SRU train on existing plant or adding a tail gas processing unit also warrants to do stack optimization. And the third one is adding a load or operating above the design load. This could happen, for example, if any plant is operating with the two trains there, and for any reason if the second train is down, first train might have to share the load. And most of the sulfur unit might be designed to operate like 10 to 20% above their design or license condition. However, the local environmental bodies approval need to be received to operate how long it should be running that way. Other thing is to reduce carbon footprint. It's a general golden rule for operating companies in oil and gas in particular is to protect the environment or do your best to get maximum efficiency and minimum impact on environment from your unit. Other is the due diligence as a part for operator and engineer of any unit to strive to make minimum impact from operating facility on environment. And this one is more interesting is saving the fuel gas and carbon tax. As I discussed before, like optimized condition could save fuel from 5 to 40% depending on facility size and operation. And this is from our experience through doing this program for several of other clients back here. And it is not only saving money for fuel gas, it is also saving money on terms of carbon tax the company might be paying for. In Alberta, starting January 1st, 2017, the carbon levy will be applied to fuel at a rate of $20 per ton. 1 year later, the levy will be increased to $30 per ton. So the carbon levy will include the price of all fuels that emits greenhouse gases when combusted. In our case, it's a natural gas. So now we'll discuss how to do incinerator optimization or what step required to do so. So there are 4 key steps. First is the basic simulation, then getting a waiver from local environmental body to do the testing and field testing and creating a plume dispersion model which represents how the unit would work if we operate it at recommended lower temperature. Basic simulation. Before we apply for a waiver or we start the field testing, SRE collects data such as present operating condition of the sulfur recovery unit, the feed stream compositions to the unit such as acid gas, fuel gas, sour water stripper gas, or any other feed streams are going there. And we also collect detailed design drawing on stack and incinerator as well. Using all available data, simulation case built to verify burn ratio, excess air, and stack top temperature. In addition, several iterations made on this simulation to access how much improvement could be made on this unit. And as I said, this is a basic simulation. It did not incorporate detailed modeling. Several field testing data is required to make a detailed model. And we'll discuss in the next slides how we can do field testing and collect the data there. Getting a waiver from local environmental body. In Alberta, it should be noted that applicant may not proceed with field study until a temporary waiver of the approved minimum stack gas exit temperature has been obtained from a year. And it could apply for different location and plant depending their local regulatory bodies. In applying a waiver, we need to apply for stack reduction temperature, top stack reduction temperature for a day, 2 or 3, depends on the size of the plant. And once this waiver approved, we can go ahead and schedule the field testing. And certainly SR is glad to help any of our client in this process. Before field testing, client must recalibrate all or re-verify all related flow meters, thermocouples, and analyzers, because these are the data we are looking for to create a model at the end, and models are as good as the data. So this is the very important parameter before we go ahead and start field testing. Second thing is to take a note about safety. Different facilities have different safety standard and procedures. And for stack sampling, SRE prefer to collect sample from middle section of the stack or at the same platform where the analyzer is located. However, it might be around at 60 feet or 100 feet, depends. So it warrants different safety standards, for example, fire brigade watch or crane or something. In general, the program consists of 2 to 3 days of field testing work in SRE. SRE collects 2 duplicate samples for every 50 degrees centigrade temperature reduction at stack top. And these 2 duplicate samples are necessary to get the representative results. In order to produce an accurate incinerator TRS destruction efficiency model, as well as plume dispersion model, accurate heat and material balance must be created. In order to accomplish this, SRU samples of feed stream needed, or in short, we take in and out of the sulfur recovery unit to assess the overall recovery efficiency of the unit. One really interesting thing over here I'd like to mention is SRE's capability of processing sample in very short time frame. SRE uses micro GC, and which can process sample in 5 minutes. So whatever sample we collected at the stack top, those sample degrades with the time. And as with the SRS this capability, those degradation time is reduced and there are less chance of compromising those samples. The SRS in-house TRS modeling software will be used after all this testing performed. And using this model, SRE determines the incinerator's kinetic design factor. We call it IKDF, which is a unit-specific TRS destruction efficiency parameter. The data on SO2 mass flow and stream velocity at stack top could be determined using other simulation models. So once the field testing completed, this is the last step in this process is plume dispersion model creation. This model could be categorized in 3 categories: screening models, detail models, and comprehensive models. The comprehensive models are multi-layers and multi-species, while the screening models are the basic models and mostly they are steady-state models, and they are mostly incorporating worst-case scenario-based situations. And this dispersion model uses mathematical formulas to characterize the atmospheric process that disperses a pollutant like SO2 in our case to the surrounding atmosphere or vicinity. Based on emission and meteorological inputs, a dispersion model can be used to predict concentration at selected downwind receptor locations. Take a note, at different facilities and different size of the facility, and depending on the local environmental body, they in general recommend which model they would like to assess or analyze based on your facility. So the body might ask you to do just screening modeling or detailed or comprehensive one. Some models have basic equations and other has a complex. However, all models are a representation of reality, not reality itself. We cannot expect a model to provide perfect results. In some situations, model may predict the actual concentration very well. However, there are so many other parameters are playing up here as well. For example, if there are some other facilities in your neighborhood, or there are other plants or refineries close to your premises, then the downwind conditions may have applied, or the client might have to collect other facilities data as well to incorporate in this plume dispersion model. In addition, the diffusion characteristics of the area should also be evaluated for typical condition in such that season of the year, wind and temperature profiles should also be obtained, and the trajectory of the plume could be determined. This case study is about a client in southern Alberta operating at approximately 60% turndown. This client's plant was designed to process for 10 tons per day, pretty small plant. However, due to turndown conditions, they were processing only 4 tons per day. A desired stack top temperature reduction we applied for is 300 centigrade to get the waiver. That means they are licensed to operate the stack top temperature at 538 degrees centigrade, and we want to study up to reducing the temperature to 300 degrees centigrade. The TRS emission limit is 300 ppm. However, being a little conservative, we will be targeting for 250 ppm. So in this scenario, client applied for waiver and they were approved to do 2 days field test study. And SRE performed 2 days field test study at the client's facility. So on the first day of the field testing, first SRE collected and analyzed the feed streams to the SRU and incinerator. The feed stream consists amine acid gas, fuel gas, and sulfur pitman gas. This SRU's incinerator had two type of air supply. The initial air supply was from the compressor. The secondary air supply was from the lower. At the initial baseline testing, we found that unit was operating 10 to 11% excess air. So SRE tried to cut that thing back down to around 3 to 4%. However, the BMS system wasn't allowing us to do, because if we are trying to close the louvre after a quarter, the BMS system was tripping on the incinerator. So that was the really limiting factor for us in terms of excess air. However, we proceed with the testing by reducing stack top temperature 50 degrees centigrade on each stage. So they were operating at 538 degree. So first step was at 538 degree. We took identical samples and create the baseline. After that, we bring the temperature down to 500 degrees centigrade and let the stack stabilize for a while and collect another duplicate sets of sample and analyzed, such that we reduce the temperature up to 370 degrees centigrade. And thereafter, we couldn't reduce it more because of there are some limitations in the terms of controllers, which wasn't allowing us to do beyond 370 degrees centigrade. However, we have enough and sufficient data and points to create the curve. Okay, so with those testing data, SRE created a kinetic design factor curve with the kinetic design factor available from SRE's in-house simulation software. From that curve and extrapolating the results, SRE find that at 325 degrees centigrade, we are getting our target of 250 ppm. So this is our set point for further study on plume dispersion model. The simulation software identified the limiting equipment units, such as manual air louvers, and there was a 2 transmitter available at the stack. However, one transmitter wasn't reporting that accurately. The fuel gas requirement decreased by almost 75%. That's huge saving. The annual saving could be $30,000, or we can say $7,500 per ton of sulfur. And if we extrapolate these results for typical 100 tons per day SRU, it could save about $75,000 annually. So in other words, by reducing the stack top temperature to 325, the fuel gas requirement drops and the corresponding annual saving could be achieved. In addition, the saving is just in terms of fuel gas. If we could add up the cost associated with the carbon tax, then the saving could increase even further. Wrapping up and questions and answers. First, what to remember about SRE is on-site problem solver. We are here to answer all of your questions regarding sulfur unit, amine unit, and stack optimization. And SRE is glad to help on any stage of this process. And I encourage you to see and check out if your unit could have a room to do improvement on this front. And the stack optimization program has payback time less than a year. So this is a win-win condition for all of 3 stakeholders: environmental body, client, and us. So now we are opening up the session for question and answer. Okay, so there is one good question here about if there would be any checkbox item or something before we proceed for field testing for optimization. Yes, definitely there is. And before we go ahead for field testing, SRE can provide you that checkbox list. However, that list is customized depending on the client's facility, and different client has different configuration, and the checkbox are created for that. So while we create the baseline model, we also submit a client the copy of that checklist, which should be performed before field testing. Other questions we are getting is, are there any notes gonna be available? Nice question. This webinar SRE will be posting on YouTube, so you can access it anytime. And if you want clarification on any point or want more information, please email us. Other questions we got is, in the case study, the site was operating at a high turn down. If client had to operate back at design, then would they still be able to use the lower stack temperature? Good question. And this question might ask to the client by local environmental body as well, as the facility was licensed for certain tonnage. SREs this field after this completing field testing and creating plume dispersion model, we can definitely extrapolate the results for design, tonnage or load. However, there are two key things to be taken a note is that for example, the facility was operating at 4 tons per day. But if we want to extrapolate it for design 10 ton per day, then we have to consider two scenarios. One is if is that 10 tons per day is with the same current lower quality acid gas or it is with the higher quality acid gas. However, SRE can extrapolate and create a model for both scenarios. Nice question. Can the stack optimization be used in a refinery? For sure. This program can apply for both refinery and a gas plant. However, if the refinery has a multiple train and feed, SRE might have to take samples from that and analyze them to create the overall model. And thank you so much everyone for joining our webinar, and please send us any questions regarding sulfur unit, amine unit, simulation or stack optimization at info@sulfurrecovery.com. The number is 403-226-5951, or you can contact me at dharmeshp@sulfurrecovery.com. My cell phone number is 403-874-4015. And to explore all of our services, please visit our website at sulfurrecovery.com. This presentation will be available on YouTube, and you can also sign up for our regular newsletters. And again, I really appreciate your support on this matter. Thank you so much.